Hi everyone, and welcome to Erik's Electronics Workbench. So on the bench today, I have this vintage Fluke 8125A digital multimeter. Now you can probably tell just by looking at the instrument that it's not your typical Fluke digital multimeter. And that's because this digital multimeter was intended to be used by the US military under some of the harshest environmental conditions. Now I've not opened up the meter, I've not tried to power it up, I have no idea what its condition is, and I noticed several issues with it that would make it hazardous to even try and power up. So follow along and let's see what it takes to put this meter back into service. I think it would be pretty cool to have this meter working and on the bench for, actual troubleshooting and testing and have it appear in some future videos. And one of the things about this meter is that it has a Nixie tube display, so it has a very nice retro look when it's actually in use. All right, so let's get started. So the condition that you see this Fluke 8125A is exactly how I received it. I haven't done anything to it yet. So let's take a closer look, see what we're dealing with, and I'll point out a few things that I've already noticed about the instrument. So the paint on the outside of the transit case, it has a few nicks and chips, but really nothing too serious. I think using a mild detergent and some water would help to clean up the paint, just make it look that much better. It has quite a bit of scum and dirt buildup from years and years of use. But overall, I don't see any dents or broken components. And the front panel looks very clean. I'm happy with that condition. There's no scratches on the display window. So overall, pretty typical of what you'd find the condition of used military surplus in. So it's nice that the transit case was never repainted because there's some markings on the top here that show a little bit about the past history of this multimeter. So you can see it says VAQ 132 and then AT shop. Someone wrote with a Sharpie right here the part number, serial number, a barcode, some kind of a tracking number, I suppose. But VAQ 132, that's the Electromagnetic Attack Squadron 132, also known as the Scorpions. And it's a US Navy aircraft squadron. And they're based at NAS Whidbey Island, which is in the state of Washington. And they've been active since 1955 until present. And of course, AT Shop, AT is the abbreviation for Aviation Electronics Technician. Now, as of making this video in 2025, this instrument's probably about 50 years old. So I don't know the exact years that these instruments were produced, but there's a Fluke catalog that's dated 74 to 75, and it does show this instrument in that catalog. So I'll put those pages up on the video now. You can pause the video if you're interested in seeing the technical specifications. Take a look at the last page. It has the price that this sold for back in the day. And if you convert that dollar amount to 2025 US dollars, it would be about $11,000. So not cheap at all when these were manufactured. So on this front portion here that goes the cover that goes on the transit case, the rubber seal is in good condition around here. It's still pliable. This little door opens up for storage inside. The fuses are still here, which is nice. Those didn't get lost. So they're just spare fuses. You can see right here, this one says instrument fuse. This is power fuse. This says internal power fuse. Then it just says input power, 115 volt or 230 volts, 50 to 440 hertz at 10 watts. I imagine that the voltage change between the high and low voltage ranges is jumpers inside of here. I don't think it's auto-ranging like a modern switch mode power supply. And I know it's set for 110, 120 volt range because it has this plug right here for standard North America, 120 volts. Now this power cord right away has an issue, so one reason I don't want to power this up. So if we take a look right here, just touched up here, you can see the plug itself looks fine. I don't see any issues over here, but this other connector is known as a Cannon plug or a circular connector. And on the back right here, you can see the wire going into that strain relief. It's kind of frayed and pulled back, and you can kind of see into the wire. It's not actually bare wire that you're seeing, it's some cords that are inside the insulation for strength. And the other side has little sockets right there. There's a keyway right up on the top for locating it when you plug it in. So that definitely needs attention. This is not usable the way it is. I wouldn't trust that. However, take a look at this right here in my junk box pile. I found this cord. So this has the correct plug that we need right there. And on this side, of course, it has the correct Cannon plug. So again, let's get that touched up for you. You can see it has that same Cannon plug. The keyway is in the same position right there. This one looks good. I don't see any problems with this cord. The thing that I don't know is if it's wired the same way. So you have the 3 sockets on one end right here on the Cannon plug, and you've got your hot, neutral, and ground on the plug on the other end. We need to make sure that the hot, neutral, and ground are going to the same 3 positions here as they are on the original cord. So we'll use an ohm meter and we'll check that. If they're not, then this isn't usable, and probably just have to repair this one. This is definitely repairable. I'm not worried about that. But if I can use this one, then that's just one less thing to do, in the meantime. Also on this front cover right here, I don't think I mentioned this little plastic piece right here, this odd looking little wedge, is so that when you put this cover in place right here, it just ensures that the power switch is pushed down to the off position. So if this is up like that, this would hit and it just pushes this down. All right, let me move this stuff out of the way here, and we'll get this zoomed in here a little bit closer on the front panel. See that okay, I think? So one of the first things that we notice when looking at the front panel is that there's a calibration sticker here that's not been broken. So it's over the head of this screw. So there's 3 screws right there across the top and 3 more on the bottom. So you take those screws out and then the whole instrument comes out of the transit case. So it's a very good sign that it has a calibration sticker that's not broken. If you've ever seen one of these stickers before, you know that if you try and peel them out of the way or do anything to them, they're tamper-proof and they tear by design very, very easily. So there's no way that you could ever peel that sticker off and somehow get the screw out and then put it back in place. The sticker would just completely disintegrate. So hopefully the electronics are in reasonably good condition. Now we have the binding post right here for the test leads. So the high, low, and ground connection has a jumper link right here for ground, so you can tie ground to low or you can float the inputs. Now there is a limit on the voltage if these are floating, how much this can float above the ground connection, or the chassis I should say. So that can't be exceeded, but nonetheless it can be broken right here. There's a connector right here for the AC line input with a dust cap, a little retaining chain. 2 fuse holders, which brings me to the next issue. Both of these fuse holders are loose. So there's no way I'd want to power up this instrument with this condition, because I don't know if these have been twisted around and the wiring maybe is broken off or something going on, or if the fuse holder itself is broken somehow, but you can see how loose that is. I don't like that at all. They don't, if I pull this direction, they don't come out of the front panel. So I don't think they're broken, but they're certainly loose. And who knows if they've been twisted around or somebody was trying to get this cap off. Again, this instrument was made for very, very harsh conditions. So there's O-rings, these extra caps on everything, keeps the water and dust out. So there's 2 indicator lights here. This says low temp and power, so this is AC power on. And low temp, if this gets down to freezing conditions, there are heaters internally that will turn on only if this is AC line operated, and it will keep the instrument warm. Of course, the power switch right here, rubber boot on the power switch. All the rubber pieces are all in very good condition. I don't see any problems, with like dried out rubber or torn rubber or anything like that. So all of these buttons across here for the range selection and the modes and everything, this rubber is in good condition. The buttons work, they're interlocked. You push one in, the next one pops out, so no problems there. Everything works. So it's manual ranging, not auto ranging. There's a filter right here, so it's a noise filter. It's an active type filter. So you have your AC volts, DC volts, ohms. Again, the range is over here. And of course the display window, and it's really hard to see on camera, but this window has a very fine wire mesh in it that keeps interference from either going into the meter or coming out. Because if you don't have that wire mesh embedded in that glass, this would basically be, just like a hole in the instrument. So they definitely want to shield the instrument internally and then externally from effects, either way. Let me grab my flashlight over here. This window is quite dark. Kind of has a yellow color to it. But if I shine this light in here, you can see right here there's actually a meter that shows battery level, and it looks like line operation level for voltage. So I would imagine there has to be a backlight on that meter, because otherwise you really wouldn't see it. And then the Nixie tubes are over here. So there's 1, 2, 3, 4, 5 tubes, and then there's a neon indicator in the middle, which forms a 1, I believe, is the purpose of that neon indicator. So it's standing vertical this way. So I'll talk a little bit more about the Nixie tubes when we get into the instrument, but a very cool retro display. This will look very, very nice when that's turned on, and just how Nixie tubes look. They have a pretty cool design to them. So I built a Nixie tube clock, and it's been going for over 15 years now. It keeps a very, very accurate time. It definitely gets a lot of attention when anyone sees it. So as I already mentioned, this has a indication for batteries right here, and I mentioned that the heaters only come on if it's AC line powered. Well, the reason is this instrument is equipped with the 0-1 option, which is the internal battery, and there's a little data plate right here. I'll put that up on the screen so you can see what it says. And that data plate is confirming that this does have the batteries. That's another concern. I really hope that the batteries in here, which are, they're long gone, they're obviously not going to work. They need to be removed, of course, but who knows if they've leaked or not, and I really hope that there's not serious corrosion because of those batteries. I believe they were NiCad type batteries, and you know, I'm really hoping that they're not leaking all over the place internally and causing a lot of damage. So we'll find out when we get the instrument opened up. Now, I'm not going to replace the NiCad batteries because I don't need another battery pack to deal with, and I wouldn't use the battery feature anyways on this instrument. When I do use it, it'll just be line powered. So for now, we're not going to worry about the batteries. They'll just need to be removed, but really hoping that we're not going to be dealing with serious corrosion issues internally. All right, so the next thing that I'm going to do is remove these screws, take this out of the case, and let's take a look inside and see what we're dealing with. All right, the screws are removed. Let's get this out of the case here and see how this looks in here. Missing screw right there. Well, not too bad. I don't see any major amount of corrosion in the case. Looks okay there. That heat shrink looks like it's a little chewed up there. Might want to take a look at that, see what's going on there. It's got a little bit of a bend right here in the chassis. I don't think that was supposed to be. Yeah, something. Ding that right there a little bit. I'm not sure how that would have ever been hit like that. I don't see any dent on the outside of that case. Yeah, not too bad though. Not seeing where the battery pack is. I'll have to get this cover off and see what's going on, but yeah, no, not too bad to start with here. Let's see. Just looking down inside here. I'll get you zoomed in and we'll get a better look here. Just kind of going over things on the first glance here, and it looks like there's a cover behind the Nixie tubes right here that's loose right here. I'm not sure. It's like a plastic cover just to, you know, keep it so it's dark behind the tubes down in here. In this corner, oh, I see what happened. Yeah, there's a screw that's missing over here. Looks like that plastic has gotten damaged a little bit, so something will have to be done over there. Looks like a minor repair is going to be needed on that corner right there. And I'm seeing one of the Nixie tubes is, it looks like it's out of place a little bit. So again, down in here, let's see if I can get you zoomed in a little bit closer here. A little bit hard to see, but the top of each Nixie tube is supposed to poke through just for some support right here, and you can see how this piece, see how that's moving in there? So that shouldn't be, and it looks like this tube is popped out of place. Hopefully that tube isn't actually broken. So I'm gonna have to take a closer look and see what's going on there. Let me get this top cover removed here and see what's going on. I mentioned there was a screw that was missing right over in here. I'll have to find out if that's floating around loose inside the case over here. Get this back out a little bit here. It's inside there. It looks okay in there. I know it's pretty dark, but I don't see. Let's turn this upside down. Well, yeah, some old dust and dirt fell out of there, but no loose hardware inside there. So anyway, yeah, let's take a closer look at this. I'll get this cover off of here, kind of inspect around a little bit more and see exactly what we're dealing with, if there's any other damage going on, and we'll take a closer look. All right, so I have the 8125A disassembled a little bit further, and it's good news, bad news time. So here's what I found so far. The good news is that the electronics look to be in reasonably good condition, so I don't see any components that look to be physically damaged, like they're broken or, you know, overheated, things like that going on. So who knows what other problems might be lurking in the electronics, and we'll get to all of that when we power up the instrument. But there's resistors in here that are precision type resistors in this area here. And luckily those haven't been damaged or broken. And there's a lot of transistors in here I'm sure are probably obsolete. And again, I don't see anything that looks physically damaged. So that's the good news, and it's actually quite a miracle that the electronics are in the condition that they appear to be in, because it looks like this instrument was dropped at some point. If you see over here, this is a pretty heavy gauge side panel. It's aluminum. You can see it's bent right here, how this bends in. This switch, is amazingly intact and not broken. And this is a slide switch. This is the switch that changes the voltage from the 115 or 230 volt ranges. So I was mentioning I thought there were jumpers, but it is just a switch that you move. So luckily it didn't crack that switch, because basically it's pressed in right here and the switch is riveted to this panel. That switch is okay, not seeing any problems there. Again, I think the instrument was dropped because there's no way that this should normally be bent like this. There's a little bit of damage on some metal in this corner that I'll need to take a closer look at. Again, it looks to be repairable, but it shouldn't be damaged in normal use. And a big indication right here is that this piece right here, which goes over that battery pack right over there, is, you can see it's kind of warped in and bent on that side. And the whole thing is basically kind of torqued over. You can see this comes up and is bent outward. And I don't know if I turn it this way, you can kind of see this is bent in right here. So there's no way that this should, in normal use would be bent. And this is a pretty heavy gauge aluminum. This doesn't bend very easily. And you can see just very minor corrosion. It was just a little bit where the batteries were touching. That can easily be cleaned up. And that's also the good news, is that battery pack over there, that's the NiCad pack, it only has a little bit of corrosion around the cells. So I'll just take that battery pack out, recycle it, get these wires disconnected, and that'll be the end of the battery pack for now. Won't have to worry about that. So this battery and everything sits on top of this circuit board, so it's amazing it didn't leak and have corrosion go down on this board. That would be a complete disaster. So those are good points, and it looks like we can kind of continue on with maybe powering this up and have a better idea of the condition electrically and see what's happening. Now, unfortunately, there's some damage right here. So this is a piece of plastic, and this corner here is broken, and over here is broken off. But there is a screw that fits right here, and that's, this is okay, and it will still hold this in place. I'd like to be able to fix this corner, because if these two screws would hold this plastic in place, then that would be a little bit more secure. This plastic is supposed to hold the Nixie tubes behind this window, so it just supports them. And right here is one of the Nixie tubes, and again, good news, none of the Nixie tubes are broken. And each Nixie tube has the little top where they pull the vacuum out of the tube. Let me just touch this up for you here. Just like all vacuum tubes have the area where the vacuum has to be pulled out, so on the Nixie tubes it's up on the top. So that pokes through that plastic piece up on the top, and it just supports it. And on the other side, the pins are brought out to this plastic piece on the bottom, and it plugs into a socket on the circuit board. So this one was just loose, just sitting in there. Really wasn't even plugged in. And again, because that plastic piece wasn't really holding it. So I need to take a closer look, to make sure that they sit securely in there. The good news is none of the Nixie tubes are broken, and they're all in place. Now this Nixie tube says Burroughs, and then it says 78-17, so most likely 1978 for the production year. And the other Nixie tubes, I think they say ITT and made in the UK. Let me look around on the other side here. And yes, they do. Yeah, they say ITT on them. So this was the only one that says Burroughs. The others are all identical with the other name on them. So the other thing that I'm noticing is that these fuse holders are broken. So unfortunately, they're not just loose, they're actually cracked. The housing is cracked on them. But I think I can power up the instrument because the break is such that I think electrically they're still going to work, but they're going to need to be replaced. And it may not be the easiest thing to replace. I might actually have to pull this whole front panel off. I'll have to look closer. That's unfortunate that both of those are broken. And I think these got broken, just something hit, on the front out here and damaged them. But electrically, they may work. I'll take a resistance reading through them and see if there's continuity. And I don't see anything that's causing a short circuit. They haven't been twisted around and damaging wiring on the other side. So it may be possible in pretty short order to try and power this instrument up and get a better idea of the condition and see if it's functioning or exactly what's going on electrically with it. This black wire right here for the batteries was soldered to the board. It's supposed to plug onto that pin. The red wire right here just plugged onto a little pin. So somebody soldered this wire. So here's one of the Nixie tubes out of the 8125A. So you can see the internal structure and how the numerals are stacked up inside. Now they're not actually stacked in numeric order because you want to see the back digits just as clear as the digits in the front. And if they were actually in numeric order, some of the digits are such that they would block the other digits and cause shadowing and kind of interference. So they're stacked out of numeric order. Definitely gives them a unique look in actual use. Now about 15 years ago, I built a Nixie tube clock. So I'll put that up on the screen now and you can see how the tube looks in actual use. Pretty neat when they're actually turned on, very eye-catching. So Nixie tubes are a cold cathode display, meaning that there's no filament. So don't confuse them with a vacuum fluorescent display or a VFD. Those work in a very, very different way. So internally there's an anode, which is actually a wire mesh. And then the characters or the symbols, the numbers and so forth, those are actually the cathodes. And the tube itself is filled with neon and perhaps a small amount of argon, and it gives it that classic orange or kind of a red-orange glow. And they were introduced back in 1955 by the Burroughs Corporation. And Burroughs used NIX1, and it said that that stood for Numeric Indicator Experimental Number 1. And if you take that, Numeric Indicator Experimental Number 1, they turned it into the word Nixie. And Burroughs trademarked the name Nixie. They owned that name. But there were many other manufacturers of the tubes over the years. And currently, they're very popular in clocks, just like I built, due to that retro look. Now these Nixie tubes take about 170 volts to strike. That voltage probably varies some with different types of tubes, but they're fairly high voltage, but very, very low current. And then once they do strike, the voltage actually can be dropped down just a little bit, so they need to be current limited, and that's done with a series connected resistor. And Nixie tubes operate on DC voltage. If they operate on AC voltage, you would get the anode and the cathode glowing, and you wouldn't want that. So it's always operated on DC voltage. Just like if you have a small neon indicator tube, if you operate it on DC, you'll see just one of the electrodes inside glow. But when they're operated on AC, both electrodes appear to glow, but really they're alternating back and forth because the AC voltage, typically 60 Hertz line voltage, makes both appear to glow. But again, on a Nixie tube, you only want the symbols or the numbers to light up, so they're operated just on that DC voltage. All right, so I disassembled the multimeter a little bit further so that I can inspect the bottom of the circuit board before trying to power up the instrument. So this panel fits on these 4 standoffs, and then this panel fits on top of that panel. Now these 6 power resistors are just used to heat the instrument if it falls down to freezing temperature. So I can leave all of this disconnected. It won't have any effect on powering up the instrument. This panel plugs into this connector right here. And we already saw these pieces where the battery was mounted. So this bracket was bent. I straightened that out, and I cleaned up the minor corrosion that was in that box. And I noticed that the battery had a date on it of 1978, so it was probably the original battery pack. Now everything looks to be in clean condition on the board. I don't see any damage to the board, like a crack or something really serious. The switches look to be in good condition. Everything looks original, so that's nice to see. And it's really amazing given the physical condition of this multimeter. This whole frame was sort of twisted and tweaked out of position. So I'm noticing some areas that are going to need attention once all the electrical is gone through and the meter is actually in working condition electrically. I'm going to want to spend some time, with more of the mechanical side, fixing the frame. There's some areas that are bent. I think this whole frame needs to be removed and straightened out. And something like this, you never want to hammer on the frame to straighten it. It needs to be pressed or squeezed. So it'll take a little bit of work to do that, but it's certainly, possible to do. And I've been looking at how it actually, comes apart and what needs to be done. So that will obviously be later on. I actually think that this whole front panel needs to be removed because the rubber piece that's around the buttons that makes them waterproof is not installed correctly, so that needs attention as well. It doesn't look like it's torn, but it's not actually installed correctly. There's sort of a second piece of metal that clamps it in place, and it's not in position, so that needs attention. Having this disassembled the way you see it gives more access to these fuses, so that's good news. I can probably get those replaced, just the way it's sitting here because you'd have access in here. However, I did check electrically, they're okay. So even though these fuses are broken, the holders are broken, the fuse element and the contacts in the fuse holder and everything are perfectly fine. There's no shorts from the fuse to the chassis. So all of this can be just left alone for initial testing. And my power cord, I checked against the original power cord, and it is the same, so we'll be able to use that cord as well for testing. And these panels have all the calibration adjustment points clearly marked, so that's a nice feature. I'm really getting suspicious about that calibration sticker that's on the front panel because, again, to me this meter does not look like something that was in the physical condition of an instrument that would have been calibrated. If someone did calibrate it, I think they really did a hasty job on it. And again, the physical condition, it's like it was dropped or something. So I have to say I'm a little bit disappointed about the physical condition inside, given that it had that calibration sticker. I've worked on other pieces of military surplus that had those calibration stickers. When you open it up, you know, they're like factory new inside. Maybe I was just getting lucky on those, I'm not really sure, but in this case, it definitely needs some attention. I don't see any reason at this point that we can't try and power this up, so we'll do that next. And just to make a mention, this is the Fluke model 8125A. I've not been able to find any tech manuals on this meter, except I do have a calibration manual for it, which is, you know, that'll be helpful. But the good news is this meter is very similar to the Fluke 8120A. The 8120A had the ability to measure current, and this meter can't do that. But the 8120A's schematic is very, very similar to this meter. And I do have the 8120A service manual. All right, so let me position things a little bit different here. Let's try and power this up. All right, let's try and power up the 8125A and see what happens. So I'll take this cover off the connector here from the line cord. And so it looks like the keyway goes down. Get this right here. There it goes. So I'm going to power this up on my current limited isolation transformer and variac. So the isolation transformer is needed for the safety, and it's current limited with an incandescent lamp, so if there's something drastically wrong, that lamp will just glow very brightly and protect from severe short circuits and overloads. So if you're following along, you're definitely doing so at your own risk. Take care and be safe. Know the safety precautions around AC line operated devices like this, and of course with the meter all open like this, there is exposed AC line. There's also about 200 volts near the Nixie tubes in that part of the circuit, so you want to be cautious of that voltage as well. So again, if you're following along, you're definitely doing so at your own risk. All right, so let me get this plugged in over here. All right, so power switch is off. I'm going to switch on the isolation transformer and turn up the variac. There it goes, set to 120 volts. All right, here we go. All right, so it's barely drawing any power, so that doesn't look like any issues going on there. So very cool. We do have some activity on the display. So now the camera, the flicker that you see on the camera right now on those Nixie tubes, to my eye looking at them, it has that flicker, so that's a bit of a problem. I don't think they should be flickering like that. Sometimes the display, you know, on a camera, you'll get a flicker that's not apparent, like on an oscilloscope display, for example, and it flickers on the camera, but not when you look at it. But in this case, it is flickering, to, you know, to my eye as well. But they do light up, and it's zeroed, so that's, you know, it's good. It's just sitting at 0. So let me go here. It's AC. Okay, so it took off the polarity indicator. And it looks like kind of jumping around a bit there. It is lighting up that other indicator that makes it the 1 right there. So see that the polarity indicator was over here, and then there's a neon lamp that forms a 1. So that's flashing. So it looks like everything's trying to light up. I don't think it should be doing that in the ohms range though. Zeros again. Let's put some voltage to it. Let me try, turn on my DC power supply here, and I'll just clip these leads on. Let's see what happens here. Okay, so I'm going to turn up the power supply. So the power supply is at 5 volts right now. No, I'm not getting anything meaningful on the display. So that definitely looks like a problem there. Yeah, that's not really doing anything. Let me flip the polarity on the leads here. Let's see, go like this. Okay, well the polarity did change, so that's a good sign. So it's able to detect that, but the numbers are completely random. That doesn't make any sense. It's only 5 volts. So yeah, there's definitely an issue going on there. Let's try resistance here. If I go, put this over here. I'm just going to grab a power resistor here. Let's see, what's this one right here? This resistor is 100 ohms. Let's see what happens. Just have it clipped on the end right there. So yeah, if I disconnect it, it jumps around, and then when I do connect the resistor, it kind of settles down. Is that? Getting a lot of 1 displays. It was kind of showing a 1 with the voltage as well. Although that actually wouldn't be completely inaccurate, because if this is in k ohms and this is, you'd have 0.1 k ohms is 100 ohms. I'll try a different resistor here. Let's try, here's a 300 ohm resistor. 300 ohm power resistor. No, that's not any kind of a meaningful display there. Just a lot of jumping around. So yeah, it definitely has some problems going on. So it's promising that the display is lighting up and all, but it's not able to read anything. AC volts, let me make a connection here, and I will tie this into my signal generator on a low AC voltage at 60 hertz. Let's see what happens on that. So turn this on here. So let that start up. Put this over to volts AC. Put this down. Put on 10 volt range. The signal generator is starting up. And let's go here to frequency. Let's make that 60 hertz. And let's make the voltage, just go 5 volts RMS. Output is on. And no, that's nothing. Turn the output off. Actually, not really any change at all. So yeah, none of the ranges have any kind of a meaningful display. So I think at this point, the next thing to start is measure some voltages around the board, see if the power supply voltages are normal. That's always a good place to start with troubleshooting, because none of the circuitry will work if the power supply voltages are incorrect. So I'll start measuring some voltages and see what I find out. So I spent some time going through the circuitry in the multimeter. So I started by testing all the power supply rail voltages, and there are a number of different power supply rails used in the multimeter, and all the voltages test within spec. So I'm not seeing any issues in the power supply sections. Now the main clock is also generated in the power supply, and its frequency and waveform look perfectly fine, so no problems there either. So then I moved on to testing capacitors. So I tested all the electrolytics and a number of the other capacitors in here as well, and I didn't see any problems. Now my capacitor tester that tests in circuit can only show the capacitance and the ESR, so it's not a completely conclusive test because it's not checking for leakage. Now I have a Sencor LC102 that would do a leakage test, but you can't use that in circuit. Now none of the capacitors tested completely faulty. A number of the electrolytics have an ESR that's a little bit on the high side, but again, it doesn't seem to be an issue. Perhaps replacing all the electrolytics would be a good idea just because of the age of the instrument. But I think for now, they're okay. For testing and just leaving them in the circuit. I don't think any of the capacitors, at least the ones that I tested, are causing any problems. So then I moved on to checking resistors, and I only checked the resistors that were in portions of the circuitry that I thought might be related to the problem that we were seeing, where the display is, jumping around and showing just random digits. So there's many resistors in here, and I didn't test all of them. But the resistors that I did test are perfectly fine. They're right within spec. So then I started measuring around. There's a number of different test points in here. And I started using my oscilloscope and just measuring waveforms throughout the multimeter. Some of the test points also have a DC voltage or AC voltage depending on the input that you're putting into the multimeter. So going through the various test points, I started to notice that many of the waveforms in here were just jumping around and really out of spec. Some of them didn't look anything like what they're supposed to, and on the schematic they show samples of what the waveforms are supposed to look like. So I thought, well, that's a lot of circuitry that doesn't look correct. I really think there's maybe one area that's influencing other portions of the circuitry. So I thought a better approach would be to start right at the input and work my way through the circuit and see exactly where the signal maybe isn't correct or where a problem really seems to start. And what I found is that going from the input through the buffer stage to the analog to digital converter, okay, so up to the input of that analog to digital converter seemed perfectly fine. So the input buffer was not an issue. But then again, when I was into the analog to digital converter, everything falls apart. It looks terrible on the waveforms. But then on the other side of the analog to digital converter, you have the display. And the display, I think, is working perfectly fine because we do get numerals coming up, the digits are displaying. They're just jumping around, but it's really jumping around because the input to the display section is not correct, which now points back to the analog to digital converter section. So I believe the problem is in the AD circuit. Now, in modern electronic devices, an analog to digital converter would probably just be one chip. In here it's half the instrument is this analog to digital converter. It's all discrete components. There's 3 integrated circuits over here, but that's only part. Well, one of them is a display driver, and the others are just part of the analog to digital converter. So again, it's basically all discrete components, and that's just the design back in the day, when this was made and how it was done. So it's interesting to look back and see, these early designs to convert from an analog input over to a digital and the display. So in taking the measurements, and I was just using my oscilloscope probe, at one point I clipped onto part of the circuit and the instrument started to work. And in fact, it was amazingly accurate in the display. And when it started to work, I disconnected the oscilloscope probe and everything kept working. It was very stable. And I'd had a chance to measure the volts AC, volts DC, and the ohms, and I was able to confirm that the instrument actually works amazingly well. So perhaps it was calibrated at some point. The accuracy is very, very close to being spot on. It does need some touching up, but amazingly and quite accurate given its condition. So then I discovered something else. When I took the oscilloscope probe and touched into part of the circuit, it started making it work, and I thought maybe at first it was a loose connection, but that wasn't the case. What I discovered is that if I take this test lead right here and touch one end of this test lead to the same test point, and the other end of this little test lead is not connected to anything. So I'm just holding one end like this, and I'm just touching this other end to the test point. It will make the meter work. If you turn the meter off and back on, most of the time it's completely jumpy and not displaying correctly. You take that test lead, or any piece of wire, and touch it to that test point, and it's like it locks in and it starts to work. Very unusual problem. So I'm not exactly sure what component is faulty at this point, but it's very easy to reproduce the problem. You can basically cycle the power, and then you can touch that test lead into the circuit. So I'll show you all of this. I'll take some measurements, and I'll show you a waveform that I really settled in on when I just sort of discovered the problem and where I think the issue is within the analog to digital converter. So with all of that said, let's take a look at the block diagram. I just want to run through just the general layout of the instrument. I think it'll help you understand a little bit more about my troubleshooting and my thought process of going through and testing in certain areas. So let's take a look at the block diagram where I think the problem is at, or at least what gets influenced when I touch the circuit board with that test lead. Touching with my finger doesn't have any effect. It actually seems to need to be, a metal, test clip like this and touch in there. But also touching it with the oscilloscope probe will do the same thing. And that's actually adding capacitance to the circuit. And I think that might be a clue to sort of the problem and what's going on. So let's take a look at the subsections of the multimeter and how those sections interact, and I'll explain my thoughts on the troubleshooting to narrow down where I believe the problem is located. So of course this is the main block diagram of the instrument, and you can see right here it says 8120A. As I already mentioned, the 8120A is very similar to the 8125A that I'm working on. It's just that the 8120A was a commercial version where we're working on this military version. And the 8120A also can measure AC and DC current where the 8125A cannot. But I'm noticing that on the schematic, the test point numbering and then what's marked on the circuit board in the 8125A, it all carries over, and the component identification numbers seem to carry over, and this functioning of the meter itself, and in the electronics is identical. So the 8120A service manual is certainly applicable to this 8125A. One of the things that I noticed that's different is the component locations in some cases are different on the circuit board, so you just kind of have to watch out for that. So taking a look at this main block diagram here, I already mentioned that the power supply section is functioning correctly. The voltage looks spot on. You can see the power supply is, of course, responsible for powering all the other sections. And the clock circuit is functioning correctly as well. The frequency is good. It's a nice square wave. And the clock drives the display section as well as the analog to digital converter. So very important. If that clock frequency is off or this not a square wave, it's distorted or something like that, that could lead to all kinds of problems. But again, nothing like that going on. So over here, this is the input, your test leads on the front panel. So the input is connected to this buffer. And the job of the buffer is to take whatever you're measuring and convert it to a range of -1 volt to +1 volt. And that range of -1 volt to +1 volt goes into the analog to digital converter. So it doesn't matter what you're measuring on the input. It could be 5 volts DC, it could be 120 volts AC, it could be 1 k ohm, 1 megohm, doesn't matter. It's ultimately converted just to -1 volt to +1 volt. Now the analog to digital converter is converting that voltage range into a digital format that ultimately drives the display. Now this analog storage that's sort of hanging off the side of the analog to digital converter, very different than what you'd see in a modern day AD converter. You wouldn't find something like an analog storage unit. But the reason they have that here is because this is taking a reading several times a second of the input, but in the meantime, you don't want the display to blank out. So you can't just update the display and flash some numbers very quickly on the display when you're reading the input and then have the display, go dark the rest of the time. It wouldn't be usable at all. So to keep the display constant between readings, you have this analog storage. So what happens is, let's say you're measuring 5 volts DC, for example. It's converted over, it goes into the analog to digital converter, it puts that reading, your 5 volts, over to the display, and it stores the 5 volt reading into this analog storage, which basically contains some capacitors and electronic switches. Then, in the meantime, when you're not taking the next reading, the analog storage voltage is read back out into the analog to digital converter and put back up on the display, and it's restored into the analog storage unit again. Okay, and then it's read back out and put on the display. And this loop over here of reading out of here and in the analog storage and putting up on the display happens much more frequently than you actually are taking input readings over here. Okay, so this is a lot of activity constantly going around over here, and then a new reading, and then a lot of activity here, and then a new reading. But ultimately, the display is kept looking very constant, and it doesn't have a flicker to it. All right, so now taking a look here at the power supply subsection, a little more detail. You can see this is the main 60 hertz line transformer, center tap right here, 2 diodes. This is about 23 volts right here, DC, filter capacitor going to ground. On the schematics, anytime you see this little arrow symbol right here, that just means the circuit ground. It's not necessarily the same as chassis ground or even the low terminal on the front panel. This is just circuit ground within the circuitry in the multimeter. And incidentally, that's test point number 1 when you're taking the readings on the circuit board, test point number 1. So right here you have this 18 volt regulator. Notice it's a negative 18 volts. So negative 18 volts, ground is more positive than this negative 18 volts right here. So negative 18 volts goes to a lot of different circuitry. That voltage looks perfectly fine, no problems there. It also, negative 18 volts drives this inverter portion of the circuit, and coming out of there you have a positive 17 volts. It goes into a 15 volt regulator, so you have positive 15 volts coming out. That goes into a 7 volt reference. You have positive 7 volts coming out. That looks spot on. I didn't see any issues going on there. You also have the 250 hertz clock, so that's the clock frequency that we see referenced up here. 5 volts, positive 5 volts right here, that's driving some of the digital circuitry in the display section. And right here, positive 200 volts is driving the Nixie tubes, so the display section as well. So looking at the display section here, you can see these are the 4 Nixie tubes. There's the 5th Nixie tube where it has the plus minus symbol. And there's also a neon indicator that forms a 1 that's not shown on here just for simplicity. So the positive 200 volts up here comes to these 4 transistors. Notice it says ring counter, and you have a 1, 2, 3, and 4, and you'll see the ring counter mentioned numerous times. That's really important. We'll get back to that. So on the Nixie tubes, again, these are the anodes up here, so you're driving the positive 200 volts and switching it one at a time onto the anodes. Down here you have a decoder driver, so you have 4-bit binary coded decimal input that's coming from the counter circuit. It's driving this decoder driver, and these are the cathodes on all the Nixie tubes, so the symbols that are in each Nixie tube. So these lines are connected to all the Nixie tubes simultaneously. So let's say like this line here might go to the 1 digit. So if it turns on the 1, it's active on all of the Nixie tubes, but only one of these transistors is switched on at a time and it sequences through. So it's basically multiplexed, a very common way to drive displays. And it's done in such a way, it's very quickly done, that your eye sees this as a continuous display, but it's actually sequencing through very quickly. And a block diagram of the analog to digital converter circuit. The main thing to note here is this ring counter. So again, the ring counter, it says 1, 2, 3, and 4, and again, we're seeing those numbers right here, and there's numerous other places that this ring counter is tied into. There's a synchronizing input that goes into the ring counter. You can see that is coming from the clock circuit. And right here is the counter. These output lines right here are what's going into this decoder driver right here. So the clock circuit is very important for a reset right there. The main thing just to note on this schematic is just this ring counter, because again, we're going to get back to this portion of the circuit. And this is very, very critical, this ring counter. It is tied into a number of different portions of the analog to digital converter, even though it's not really shown here completely. There's also a 5th output. This shows 4 lines right here, but there's a 5th reset. It's marked as Z on the schematic, Z as in Z or Zulu. And then over here, you can see this is the input. So this is that negative 1 to 1 volt input that's coming from the buffer. And here's that polarity sensing circuit. And we already saw early on that the plus minus symbol was functioning. So we know that the polarity circuit is working. We must be getting an input right here. It was able to detect that. And I verified this is the right range of input. And again, this portion is working. All right, let's take a look at this next block diagram right here. So this is just a table summarizing that buffer output. So you can see in positive volts DC function, you're actually getting a -1 volt. It inverts it because of an amplifier. That's going into the analog to digital converter. The negative DC volt input, if you have the polarity flipped on the front panel, you're getting a +1 volt full scale into the converter. In the ohms range, -0.7 volts full scale, volts AC +1 volt. So as I already had mentioned. DC voltage mode, resistance mode over here, and the AC volts. It's essentially just, these are the buffer circuits, and this amplifier is the same amplifier in all cases, and it's just being reconfigured for the different functions that the meter has. So we don't need to get into a lot of this because, again, these circuits are all functioning the way that they're supposed to, but I just wanted to put them up on the screen. You can pause this, if you want to study them a little bit closer. So this is the ring counter, or at least part of it right here. It's part of the analog to digital converter, but this is the bulk of the ring counter circuit right here. So I've highlighted these portions of the circuit, and what these are on the circuit board itself are test links that can be broken. So the purpose of that is that you can isolate the outputs of the ring counter where they go off to the rest of the circuitry if you think there's a problem and if it's loading down the ring counter. All right, so very convenient that they did that. And right here is this Z, which is the 5th output as well. So take a look at this waveform right here. This waveform is really important, and we're going to take a look at the oscilloscope next, and you're going to see this waveform basically in the correct way, and then how it's not supposed to look. So it's taken at test point number 3 right here, but you can take this waveform and read it off at these test link jumpers as well. Now, here's what happens. Because this ring counter is such a critical portion of the circuitry, when everything in the analog to digital converter was basically not looking correct, I was looking for something that seemed to be common and could influence so much of it. And this ring counter is where I started to narrow in and think that there could be an issue because it is so important. Now, there's obviously other signals and portions of the circuitry that are very important, but this ties into so much of the analog to digital converter. So this waveform right here, I would say of all the waveforms, looked the worst. Okay, and that was another reason why I thought there might be a problem going on here. Some of the other waveforms were jittery and kind of jumping around, but they were there. This one really had some issues going on, and again, I'm going to show you that in just a moment. So I was taking some readings around here, and there's several tests that you can run. You can actually put a DC voltage into this, and it shuts off the ring counter, and you can measure some voltages coming out, and that all checks out fine. I don't see any issues, so we don't actually have a shorted transistor or anything like that going on here. But when I went to the test link number 1 and put the scope probe on that, the meter started to work. And I thought maybe it was an intermittent connection, but it's not. Because if you touch the test link number 1 with just a test lead, or like I already mentioned, a piece of wire or something like that, you can make the circuit basically settle down and start to function. So it seems to me that this circuit is oscillating very badly and is unstable, but becomes stable if you're able to sort of, I don't know, maybe we say trick it or make it lock in somehow. Now maybe there's a synchronizing signal over here, and I'm not sure, maybe there's an issue with the synchronizing signal. I haven't investigated close enough to see if there's an issue with this signal and how it's related to the ring counter, but I really doubt that. The signal is there. I have seen the signal, but it doesn't matter if you touch the other test link jumpers. I can't get the same effect, but test link jumper number 1, touching it with that test probe makes the counter, or makes the whole meter work. So I don't know exactly why that is. It's basically adding capacitance to the circuit would be my guess. I believe that's what's happening. But what component is actually faulty, I really don't know at this point. So I'm going to have to do some more troubleshooting. But I want to show you this waveform, and I'll turn the unit on, I'll put you up on the oscilloscope, and you'll see how poor this looks. And remember how the display early on in the video was jumping around and just gibberish on the display? And you'll see this waveform at that time. And then I'm going to tell you when I touch this test link jumper, and you'll see this lock in and look perfect. Basically, this is, you can see this step right here. Let me zoom in a little bit closer there. So you can see I'll set the oscilloscope up the same way, 10 volts on the vertical and 5 milliseconds on the horizontal. So you'll get the same reading, the same look on the oscilloscope. So you're supposed to have about a 10 volt step on this falling side right here. And we do get that. It looks perfectly fine. There's not supposed to be a notch in the center, so it comes up, it's flat, and comes down, and repeats again. And when it's working correctly, there is no notch, but check out the notch when it isn't working correctly. It's absolutely horrible. So that's a big sign of a problem. But then it completely goes away. But that notch was a clue that I thought maybe this circuit wasn't working correctly because of how poor that waveform looked. And then there's little steps, or right here in this trailing edge right there, and those look perfectly fine. There shouldn't be any spikes right in this area, and there's a number of small spikes when it's unstable. The service manual mentions that oscillations can create those spikes, and no doubt it's oscillating because it's so unstable until it locks in. All right, so let's take a look at the oscilloscope, and I'll show you exactly how these look, with the actual readings, and we'll continue on with the troubleshooting. All right, so the Fluke 8125A is powered up, and I have a DC voltage connected to the input, but the display is very random and it's just jumping around like we saw earlier in the video. Now the oscilloscope is connected to test point number 3, and the ground is connected to test point number 1. So you can definitely see on this waveform there's some issues going on. It doesn't really look like the waveform that's shown on that schematic. So for one thing, this pulse right here has a big spike that drops down in the middle, so it almost looks like 2 separate pulses, so that spike in the middle shouldn't be there. And on the trailing edge, there's an extra pulse as it's dropping down right there. Almost looks like some noise or something going on. And the service manual mentions that if that occurs, it can be a sign of an oscillation. So that shouldn't be there. Now, on this trailing edge, as it drops down, and then you have 3 more pulses that are very small, that's normal. Those should be there. All right, so now what I'm going to do is take this test lead right here. So I already showed you, it's just this wire. And I'm going to just hold one end like this. I'm not going to touch the metal. I'm just going to hold it. And I'm going to take the other end and I'm going to touch it to test link jumper number 1. All right, so reach over here. And right now I'm touching it there, like so. Okay, now I'm not touching it anymore. You see, it's completely disconnected. And look at the waveform. It's perfectly normal. Now I'm going to do this again, and I'll put you down on the meter, and you can see the result, as I do it on the meter. But for one thing, the display is normal. It's reading the power supply voltage that I have connected, and the waveform looks perfect. That's exactly how it's supposed to look. So the spike is gone, the noise is gone, there's our 3 extra pulses there. Everything about that is spot on. Look how stable that is. It's beautiful, no problems. So the question is, what is going on in that circuit that just touching that one jumper can solve the problem and basically make that circuit stable and work? Now, here's the thing, and I've seen 2 different things happen. I'm going to turn the power off. Okay, so now the multimeter is turned off. And I've tried the different combinations. I've waited an hour, I've waited, 5 minutes, it doesn't seem to matter. I'm going to turn it back on, and likely it will be unstable again. But I have seen it a couple times remain stable, but more often than not, it's unstable. So here we go, turn it back on. And yes, see, as before, it's unstable. See, settled right back in with the problems. So if I take the jumper and touch it again right here, number 1, like that right there. There it is. Perfect. Well, it's easily correctable, but that's not very convenient. I don't know what the problem is. It's very strange, that's for sure. So I guess if you want to just touch a jumper wire in there all the time, you can make the thing work, but we're going to have to do better than that for the repair. So again, I'm going to put you down on the meter, and you can see me do this and touch the circuit board jumper, and you'll see the display start working when the meter basically locks in and is working the way it's supposed to. And while it's on the oscilloscope right now, I'm just going to move this test lead over. So this is now on test link number 1. Okay, perfect. Test link number 2. Perfect. Test link number 3. No problems there. Test link number 4. That looks good. I'm going to go back actually again. I noticed something on number 2. Look at the second pulse on number 2, and I don't know if this is a problem or not, but this pulse is a little more obscured in there. You have a nice pulse there, and then 1, 2, and 3, and I don't like the way that looks. Maybe that's an indication of something. I'm going to take a closer look at that. I actually did not notice that when I last did this, or the first time when I was trying it. So that's interesting, because now, again, let's just compare here to test point number 3. You could almost say that pulse, the first pulse now, maybe doesn't look as sharp. Number 1, those all look really good there. But number 2, see that pulse in the middle now is just maybe not as clear as it should be. So on number 3, number 4. There we go, sorry, I lost the connection there. Number 4. There it goes. That one almost looks the best out of all of them. So actually what would happen is that if you're taking these readings and you put all of them together, they would just be shifted in time. You're not able to see that when I do one at a time, but really these waveforms would all be shifted. It's the outputs of the ring counter, okay? So again, let me put you down to the meter, and you can see it go from not working to working just by touching that one point. All right, so that you can see what actually happens on the meter when I touch a wire to that test jumper link. So the link is right here, just touching it with the end of this insulated tool. So this is link number 1, and then there are 3 other test links over here. So the purpose, again, of those links is that they can be cut and then breaks part of the circuit on the ring counter, actually the outputs of the ring counter, and then you can just solder the link back together again. So there's 2 capacitors right here. The link is right next to it. So I have 10 volts from my power supply connected to the digital multimeter, and it's on the volts DC setting, 100 volt range. So here we go, turn this on. So you can see how the display is flickering. To my eye, it's flickering just as much as you see on the camera there. So it's just jumping around, no meaningful readings. And come over here. So again, just taking this test lead, and I'll keep one side. I'm just going to keep it right here just so you can see my hand. See right there like that. And then this side right here, I'm going to touch right here. Okay, and there it goes. So now the display is very steady to my eye looking at it. It still looks like it's flickering a bit on the camera, but let me see if I can very carefully, I'm going to unplug this ground wire over here, don't need that. I'm just going to move this up right here. So there you go, 9.96 volts. Again, I have 10 volts connected, so very, very close on the reading. You know, just some calibration would bring that right into spec. So if I go to 10 volts there, see how it puts the 1 up there? That's just that neon indicator. It forms the 1. And then, so 10 point and then 0, 0. The 100 volt range, 1000 volt range, so you can see the decimal points moving over. Incidentally, the decimal point is not driven through that decoder chip. The decimal point is switched mechanically with these switches. So I've gone through the volts AC range is very close to being accurate, just needs a little bit of a touch-up, and the resistance ranges are very, very close as well. So I'm very happy to see that the meter can work, but the real question is, why is it so unstable, and then just touching that 1 point is able to make it start functioning? It's just a very unusual, you know, sort of a problem. I haven't really come across a circuit that's acted like this before, but I've certainly heard of problems where usually it's an oscillator circuit, let's say a crystal oscillator, and you get near it or you touch it and you influence it, and it's really it's the capacitance that you're introducing into the circuit that can affect things. I believe that's what's happening here, but I need to track down what component is actually faulty. Obviously there's some capacitors in the circuit, but the purpose of those capacitors, I don't see how one of those being faulty is going to cause this oscillation, but perhaps it's time to start removing some components and taking some readings out of circuit. I'm just going to have to take a closer look at some of the components. And I'm not so sure if moving any of the components, let's say the ring oscillator in the number 1 test links, let's say that's the number 1 output, swapping a transistor on the number 1 output with number 2, I don't know if that would, possibly that would help, if maybe that made it move over to touching test link number 2 instead of touching number 1. That might help to, you know, confirm a faulty component that way. The problem with that is that's a lot of desoldering and then soldering on the board. I really don't like that idea. You know, I have the desoldering tools, but I don't want to lift up a trace or cause any damage to the board. So I don't like the idea of swapping around a bunch of components on the board. So again, I'm going to have to think about, you know, the troubleshooting and what needs to be done next, but nonetheless, you can definitely see the result here and where we're at so far. If I turn this off, back on again, see how it's immediately just random, you know, it doesn't work again. So, very strange, interesting problem. So I spent some more time going through the circuitry in the ring counter. So that's this area of the board right here. And I tried several different things. So first of all, there's a DC voltage test mode that's listed in the service manual. So essentially you just put a jumper link between 2 test points on the circuit board, and it makes the ring counter just go into a static mode, and you can test the various voltages around the transistors. So I did that test, and everything is spot on. I don't see any issues whatsoever. So then the next thing that I did is I checked all the components again in the ring counter. So the capacitors, the resistors, and I checked the transistors with the diode test mode on my multimeter. And everything, again, tests perfectly fine. I don't see any issues. So then looking at the back side of the board, in this area, I noticed that there was some flux residue, and there were several traces very close together. The flux was kind of covering. Now, I don't know if that flux was from a previous repair, or maybe it just wasn't cleaned off at the factory. The solders in that area look to be factory original, and I don't see any components in this area that look like they've been changed out, so it may have just never been cleaned off. Now, the reason that I didn't want that flux on the board is because flux can attract contamination, so it might get fine metal particles into it, or moisture, things like that, and it can cause a leakage current on the board. Definitely don't want that happening. So I just cleaned it off with isopropyl alcohol, so that's been taken care of. So also in this area of the board on the back side, there's a coax cable that runs along that point, and it looked to me like one of the component leads that, pokes through the board and where it's soldered, and that's, they're needle sharp. It looked like that component lead had pierced into the insulation of that coax cable. Now, I tried to test with an ohm meter, and I couldn't confirm that it had actually caused a short circuit, but it was right on that ragged edge of maybe being a problem. So I trimmed the component lead shorter, and I put a little zip tie around the coax, so that basically just covers the area that was a concern, and it kind of stands the coax up off the board just a little bit as well. So that's been taken care of, but I don't think that was any cause of a problem. So then I went through and I rechecked all the power supply voltages, looking very close in this area again at the voltages. But again, testing all of the voltages in the multimeter, and not only checking the voltage levels, but also looking at ripple on the oscilloscope, and I don't see any issues. Nothing stands out as a problem. Now, I already mentioned that there's 4 jumper links that are in this part of the circuit on the ring counter, and I opened up each of those jumper links. That isolates the output of the ring counter from the circuitry that it's driving. And I don't see any problems with the circuitry downstream, so to speak. Again, the circuits that are being driven by that ring counter. Nothing's causing excessive loading or causing any readings that look out of place. So I went ahead and resoldered the jumper links back together, so they're back to the way that they're supposed to be. And then there's an electrolytic capacitor right here. So I pulled it out of circuit. Now, previously I had mentioned that I tested all the electrolytic capacitors in circuit, but I went ahead and pulled it out of circuit, and I tested it on my Sencor LC102. So here's the capacitor right here. And this capacitor does not test very good out of circuit, all right? So it has excessive leakage current. And that was a concern when I saw that, because if we take a look at the schematic right here, so we've seen this before, this is the ring counter schematic. That capacitor is right here. And it's listed as a 5 microfarad C21, but the actual capacitor says 6.8 microfarad. But nonetheless, the reason that I wanted to test this and thought that maybe the leakage current was, the capacitor has that's able to pass through it, essentially it's becoming a resistor, is because this line right here, it says TP11, test point 11. If we follow that line back, you see how it goes to the 46.4 k ohm resistors. So this has minus 18 volts on this line. And it's applying a bias up to the base of all of these transistors. Well, if we look over here on this capacitor, assume that there's, replace the capacitor with a resistor, basically a very high value resistor. You would have a path that comes over here to ground. This is a 1 k ohm resistor. It wasn't marked on the board, but I wrote that in because, or it wasn't marked on the schematic, but it is a 1 k on the circuit board, so I filled it in here on the schematic. But at any rate, if this capacitor is becoming leaky and acting like a resistor, it could be pulling this line down to ground. And when I noticed that that was something that could be happening, and maybe it's upsetting the bias on these transistors, or something's going on there, I thought it would be a good idea to at least check that capacitor. And when it tested leaky, I thought, well, maybe I'm onto something here. Well, you can see this capacitor right here I put into the circuit. This is a 10 microfarad, and so that's not quite the right value. However, everything that I've done so far that I just mentioned, nothing has changed how the ring counter functions. So it's still very unstable. When you turn the instrument on, it's jumping all over the place. It seems to be oscillating. And then touching that jumper link number 1 is able to quiet the thing down, and it locks in and it works okay. And even with this 10 microfarad capacitor, it does function. And changing that capacitor out didn't make any difference. And yes, I did test this capacitor. It tests very, very good. There's no problems with it. Now, I'm going to replace this electrolytic capacitor with the correct value. I don't like having that incorrect value in there. And in fact, I'm going to replace all the electrolytics in the whole instrument. There's not that many actually, but if this one is testing faulty, the others are probably well on their way out. The instrument's about 50 years old anyways, so they've probably seen better days. So I'm going to get the electrolytics ordered up. I think it would be a good idea just to get those all replaced. Now, going back to this electrolytic right here, let's take a look at this on my Sencor meter, and I'll also show you testing this on some other meters as well. If you're new to electronics, you may have heard discussions about testing electrolytic capacitors and capacitors in general, but often electrolytics, and you hear testing them in circuit, testing them out of circuit, looking at leakage current, ESR, the capacitance value, and then using different meters. What if you use like your digital multimeter? What if you measure it with a dedicated capacitance meter? What are the kind of the pros and cons of each? So let's take a look at several different meters that I use routinely, and I'll just run through very quickly on just kind of an overview, pros and cons of each meter, and hopefully that'll help you with your troubleshooting and determining if you have a capacitor that is in fact faulty. So let's do that next. So here's several meters that I often use for testing capacitors. Now the Sencor LC102 is on the shelf next to me, and I can't move it over here on the bench, so we'll look at the Sencor in just a moment. Now, none of these manufacturers are in any way a sponsor of the channel. They're just meters that I often use and find work very well. Now, of these three meters, my go-to is this Peak Atlas ESR 70 Gold. For testing pretty much all the electrolytics that I ever come across in projects and repairs, this is the meter that I start with. It can test in circuit, which is extremely handy. It does not do leakage testing, which we'll see in just a moment on the Sencor LC102 and why that's important. But again, this is a very quick and easy meter to use, so it's pretty much my go-to. However, it does not test capacitors that are extremely small in value, like a nanofarad and picofarad type range. So for very small value capacitors, I'll either use the Sencor or the Keysight or something like the Fluke 8225A. Now, starting with the digital multimeter, the Fluke 8225A, many digital multimeters have a built-in capacitance function, so that's probably one of the most commonly used ways to test capacitors is with a digital multimeter. But it does have a drawback. So right now you can see the numbers that are just changing right now on the display. That's just the lead capacitance. If I touch the leads together, it ends up just going to the over range. So this is the capacitor that I took out of circuit, and it's marked as a 6.8 microfarad, 63 volt. Quite a high voltage rating for such a little capacitor, but if I touch the leads across it like so, you can see it says 8.78 microfarad. So you might think, well, that's okay. I mean, the capacitor seems to have capacitance, and do we keep using it, or are there any problems with it? Well, that's not a completely conclusive test. We don't know anything about the ESR or the leakage. And there's also another test on the Sencor that's the dielectric absorption test as well. So obviously some more tests that can be done, and there's no way that you can do that with a digital multimeter. But something that you can keep in mind is that if you take a reading on the capacitor and it's suspiciously high in value, perhaps many times more than you might expect, that's a sign that the capacitor is becoming very leaky. So you can detect extremely leaky capacitors with a typical digital multimeter type capacitor tester. It has to do with the way that the tester interprets the capacitance value. When these become leaky, they act like a resistor, and it basically skews or throws off the reading that this is able to interpret. So that's something to keep in mind when you're using a digital multimeter to test capacitors. Capacitors never age and get better with value, and increase in value. So always keep that in mind. So the Keysight, which is an LCR meter, let it start up here. There it goes. You can see that on the screen there. Yep, backlight's on. So with the LCR meter, I'll just connect this on here. All right, so just clip that on there. It'll auto-detect the component. And we can see it says 6.6, basically 6.66 microfarad. So again, it appears to be a pretty good reading, a little bit closer in value than what this was coming up with. Now, an LCR meter has the ability to test at different frequencies. So, backlight turned off there. This is testing at 1 kilohertz by default, and that's a very common frequency to use, but it can test, say down to 120 hertz and maybe up as high as, I think, 10 kilohertz and some other ranges as well. And that will affect the reading that you get. So that's a very handy thing to do, and be able to vary that frequency, where on a digital multimeter like this, you're not changing the frequency, of the reading. But again, we don't know anything about the ESR or leakage, other things like that. Of course, LCR meter also tests inductors and resistors. Now on this meter, go ahead and turn it on. So it just says on the screen, monitoring for a component. And we get the result. So you can see on there, capacitance 7.64 microfarad and ESR of 3.2 ohms. So now we know that ESR and 3.2 ohms, it's a little bit on the high side. It's not terrible, but it's probably going to be higher than what a new replacement will be. Now, the ESR is an important value. It stands for equivalent series resistance. As the ESR rises up, and it will get higher as capacitors age, sometimes extremely high, it can kind of tell you the health of the capacitor. So as the ESR rises, the capacitor ends up running hotter and hotter. Now, a capacitor like this in circuit is very small signals going through it, so you're not dealing with high ripple and things like that. But let's say it's a capacitor that's in a switch mode power supply. A high ESR is a disaster, and it'll probably quickly fail if it was still put into service. And oftentimes, capacitors that have already failed, the ESR will be practically off the scale. So you can quickly tell if a capacitor has problems by that ESR reading. So it's a good thing to measure and to know. So very handy that this comes up with that value. And we can see that the capacitance that this measured was pretty much in agreement with these two meters as well. So now let's go over to the Sencor meter and we'll take a look at a little bit more thorough test on this capacitor, and you'll see why I decided that nope, it is faulty and needs to be replaced. All right, now let's use the Sencor LC102 to test the capacitor. So I've already done the lead 0 open and short calibration, and the capacitor is attached to the test leads right there. And I've entered information into the meter so that it knows the value of capacitor that we're testing. So it's set to the aluminum electrolytic mode. Capacitance value, 6.8 microfarad. So that's just the target value, so it knows what the capacitor should be. I have the tolerance set as plus minus 20%. I don't know if that's exactly correct for this capacitor, but it's close enough. A lot of electrolytics are rated right around that range of tolerance. And again, that's just part of the go, no-go testing. And then the voltage, 63 volts, and that's for the leakage test. And again, this capacitor is rated 63 volts maximum. You can see that value over here as well. And that's really where this meter shines, is that ability to do the leakage test and put that voltage onto the capacitor and actually test it under actual voltage conditions, where, as you saw with the other meters, they cannot test for leakage. And you'll see in just a moment how important that test is. So if I do the capacitance value test right here, 6.83, 6.84, so really spot on, no problems there. It does say good. So just going by the value of capacitance, you would say, oh, well, the capacitor is perfectly fine. And we already saw that with the other meters. They were all indicating a value that was very, very close to the rated value. Now, if I go over here to the ESR, we already saw that reading on the other meter. And here, 2.7 ohms. Says that it's good, and it's able to determine that that's a good reading because it knows the capacitance value. And there's basically charts that show you the ESR versus the capacitance value. Larger values of capacitors, something like, let's say, a 10,000 microfarad capacitor, it should have a much lower ESR than something that like a 1 microfarad capacitor. So again, this basically has that information built into it. So again, ESR is looking perfectly fine on this capacitor. I mean, it may be a little bit on the high side, but it's not totally out of spec. Now this will do the dielectric absorption test. If I hold this down here, it'll compute that test. So it says 6% good, so really not seeing an issue there. Now here's the capacitance leakage test. So this is set to current, and we can also do it as a resistance across the capacitor. But for the current test, it'll tell you if it's faulty or not, where it will not do that in the ohms test. So I'll hold this down here. So now it's actually putting 63 volts on the capacitor. And you can see the value in microamps over there, 118, 113. So it starts to fall, that's normal. But it does say that it's bad. So that value is remaining much too high. So it initially starts as a higher current because the capacitor has to charge, but it should basically fall near zero. Electrolytics always have some leakage current, but this is excessively high. So, it's remaining way too much current through that capacitor. Even though it's in microamps, it's still too much. And you can see that, it does say bad on the display. Now, if I go to ohms right here, it'll just basically convert that current reading over to resistance because it knows the voltage, and when you know voltage and current, you can compute resistance. So if we do this again, it'll just tell us what the resistance of that capacitor is. And as I mentioned, the capacitor is basically returning into a resistor when it becomes leaky. And you can see right there, so 828 k ohms, 832. So just imagine putting, an 800 and about 850 k ohm resistor in that circuit. That's going to have an effect. It's a high value, but nonetheless, it can't be ignored. So you can clearly see the capacitor has a problem. So definitely faulty, needs to be replaced. So I hope this gives an idea of the different ways that you can test a capacitor, and ultimately knowing the leakage test on a capacitor, the leakage current, or ultimately you can convert it over to the resistance across the capacitor, and really how important that is in determining if a capacitor is usable or not. All right, so this concludes part 1 on the Fluke 8125A digital multimeter troubleshooting and repair. So I hope you've enjoyed following along on the work that I've done so far, and if you have, you can let me know by giving the video a thumbs up. And if you're enjoying the videos on this channel, don't forget to subscribe. There'll be many more videos coming up in the near future. Remember to tap the bell symbol to be notified when I do post a new video. And stay tuned for part 2 on this Fluke 8125A. There's still quite a bit to do. I need to continue with the troubleshooting, get this thing back into working condition. It will need to be calibrated, and there's some mechanical issues that need to be addressed as well, so quite a bit still to do. All right, until next time, take care, and goodbye for now.